Okay, so today we're going to start a new chapter on L'Hopital's rule. So in the Stewart textbook, you'll see it's the next little subsection after implicit differentiation. Okay, so firstly, L'Hopital's rule is used to evaluate limits that have an indeterminate form. So we saw a bit of this previously when we did limits, when we had that infinity over infinity. Right, like the x squared plus 1 over x squared plus 2, for example. We had to factor out the x squared and then we got our answer. So we're going to continue with that and look at more difficult examples. So what is an indeterminate form? Okay, there's a few examples of what an indeterminate form is. So again, last time we saw that infinity over infinity, that was an indeterminate form. But there's others like that. So we have 0 divided by 0. Okay, that's an indeterminate form. Infinity over infinity. 0 times infinity. Infinity minus infinity. 0 to the 0. 1 to the infinity. And infinity to the 0. Okay, these are all indeterminate forms, which means just given that, you can't really tell what the value is. There's some more work you have to do to figure out the value. Okay, again, like we had with that example, limit x goes to infinity, x squared plus x plus 1 over 2x squared minus x, for example. So if you just substitute infinity, it's infinity over infinity. But that doesn't mean the limit doesn't exist. The limit does exist. You just have to do some extra work. In this case, you would take out the x squared, take the limit, and you end up with a half. Okay, so just because it's infinity over infinity doesn't mean the limit doesn't exist. Sometimes it won't exist, but it's not automatically does not exist. Okay, in this case, it was infinity over infinity, but the limit still had a value half. Okay, so those were the simple examples that we looked at last time. Now we're going to look at these other ones over here. Okay, this 0 times infinity, infinity minus infinity, and so on. How do we evaluate limits that end up like that? Okay, and for that we use L'Hopital's rule. Okay, so what is L'Hopital's rule? Now it's a bit wordy. Okay, it looks quite complicated, but when you're doing it in practice, it's actually very easy. Okay, but the setting up looks difficult. Okay, let f and g be functions defined on an open interval AB. Okay, and differentiable, so we know what that means. Okay, on AB, but possibly without a point C. So from A to B, these two functions need to be differentiable, but at some point C on the interval, it might not be. Okay, so we remove that point out, and then it must be differentiable. Okay, so that's the setup. We need that to be true. Then, if the limit as x goes to c of f of x is equal to the limit as x goes to c of g of x, if these are both 0, okay, so you have the limit of f of x, that's 0, limit of g of x, that's also 0, or plus or minus infinity. So either both of them are 0 or both of them are infinite. Okay, so if that's the case, and g prime of x is non-zero for all x in AB, and again, minus this point C. Okay, so we know G firstly must be differentiable on that interval, maybe not at C, so we remove that. It must also be non-zero on that same interval. So differentiable on the interval, and non-zero on the interval. Okay, you have to check that. If that's not true, then you can't use this. Okay, then we have that the limit as x goes to c of f of x divided by g of x is equal to the limit as x goes to c of f prime of x over g prime of x. Okay, and this is the important part here, so put a nice box around that. Okay, and as always, when we're dealing with limits, the limit must exist. So I'll add that here, but you know, when you're dealing with limits, the limit must exist. So here, just keep in mind the limits must exist. Okay, so we don't have to always write that, but in the back of your mind, just keep that in mind there. Whenever you're dealing with limits, the limit must exist, right? To write that down. If the limit doesn't exist, well, then L'Hopital's rule isn't working for you. Okay, now all of this, again, it's a bit wordy, looks a bit complicated, but what we can do is take this and convert it into 4 conditions that need to be satisfied. So instead of memorizing all of this, we have 4 conditions that you need to check. If all of the conditions are satisfied, then you can use L'Hopital's rule. If the conditions are not satisfied, then you can't use L'Hopital's rule. Okay, so it's a little bit easier than checking all of this. Okay, so conditions. Okay, so these must always be checked before you start using L'Hopital's rule. So firstly, the limit as x goes to c of f of x must be equal to the limit as x goes to c g of x. This must be 0 or plus or minus infinity. Right, that was one of the conditions from that word statement there. Okay, so that's the first thing you check. If that's not true, well, then you move on. L'Hopital's rule cannot be used. Okay, so once you've checked that, if that's true, then you can check number 2. If number 2 is true, then you can check number 3. You go down the list. If any of them is not true, then you can't use L'Hopital's rule. You have to use something else. Number 2, f and g are differentiable. Okay, again on that AB except at a possible point C. So differentiable except at x equals C. Maybe, right? Might not be, might be, but you do need to check that. Number 3, g prime of x is non-zero for all x, and again, possibly not C. And lastly, the limit as x goes to C of f prime of x over g prime of x exists. But if you end up with something, D and E does not exist, then that condition is not true, and so you can't use L'Hopital's rule. Okay, so you must always check these 4 things while you're doing the calculation. Again, if any of them is not true, L'Hopital's rule does not work, you need to try something else. Right, like the squeeze theorem that we looked at before, the limit laws, something else like that, but not L'Hopital's rule. Okay, and then big exclamation mark. These conditions are important. Okay, and we'll have a look at a few examples where if you ignore some of the conditions, your answer is completely wrong. Okay, so for example, the first problem, we'll see maybe the functions are not differentiable. So if you use L'Hopital's rule, you get one answer. If you use a method we learned before, you get another answer, and they don't match up. Or maybe number 3, you don't check number 3. And again, using this method, you'll get one answer, which is wrong. Using another method, you'll get the right answer. And again, there's that mismatch between them. So it's always important to check the conditions. Okay, so what happens when you ignore the conditions. Okay. And we've got some examples on what happens if you ignore some of them. Okay, so let's look at example number 1. We're going to have the limit as x goes to 1 of x plus 1 over 2x plus 1. Okay. Now, this looks like a L'Hopital's rule problem, right? You got some function at the top, some function at the bottom, you got a limit. Okay, maybe let's just use L'Hopital's rule. So what we're ignoring is condition number 1. We're not checking that the top and the bottom are infinite or 0. In this case, the top is not 0 if you substitute, and it's not infinite. The bottom won't be 0, won't be infinite. So condition number 1 over there, we're going to ignore that, and we're going to see what happens. So this is equal to question mark, because it's not equal to, there's a problem here. So let's try use L'Hopital's rule by ignoring condition 1. So this is going to be the limit as x goes to 1, x plus 1 derivative over 2x plus 1 derivative. So this will be the limit as x goes to 1. The derivative of the top, that's going to be a 1. The derivative of the bottom, that's going to be a 2. So this is a half. Okay, so we ignored condition 1. We didn't check any conditions. We just used L'Hopital's rule and we got a half. Now that's wrong, because this limit, we can just substitute 1. There's no issues with asymptotes. There's no problem like that. So in fact, the limit as x goes to 1 of x plus 1 over 2x plus 1 is equal to 1 plus 1 over 2 plus 1. So that's 2 over 3. Now that's the correct answer. L'Hopital's rule in quotes, because we didn't check the conditions, gave us a half, which is wrong. Okay, so if you ignore condition 1, you're going to get the answer wrong. So here, please make sure you check condition 1. Okay, so it's a nice tool to use, but you can't use it on everything. Sometimes you can, sometimes you can't. You need to know when to use it. Okay, number 2. We're going to have the limit as x goes to infinity of x plus sine x cos x all over x plus sine x cos x e to the sine x. Yeah. Now this looks very complicated. We've got some complicated thing at the top, some complicated thing at the bottom. Okay, you might want to use L'Hopital's rule to take the derivative on the top and the bottom. But notice, x plus sine x cos x is repeated at the top and the bottom. So we can actually just cancel that. So this is going to be equal to the limit as x goes to infinity of 1 over e to the sine x. But sine x, that's going to go between -1 and 1. It's going to oscillate, which means this limit doesn't exist. Okay, it always goes -1 plus 1, -1 plus 1. It never goes to some limit. So this limit does not exist. Okay, that's the correct answer. Limit does not exist. However, if we try use L'Hopital's rule, we'll see that we get an answer of 0. Now you might think, okay, we use L'Hopital's rule, we got an answer of 0, that must be correct. But in this case, it's not correct because the limit doesn't exist. But L'Hopital's rule is going to end up giving us 0. Okay, so let's check that. So this is equal to, again, question mark. This is very incorrect, but let's see why. So this is going to be the limit as x goes to infinity. Now we're going to do the derivative of the top and the bottom. Okay, I'll leave that for you to do. So we end up with 2 cos squared x over 2 cos squared x e to the sine x plus x plus sine x cos x e to the sine x cos x. Right, so in the bottom, it's just the product rule and chain rule. I'll let you do that as a little homework exercise. But in this case, when we take the limit, this is going to end up being 0. Okay, so you can check that. So you'll take the limit and you end up with 0. But this is completely wrong. The limit actually does not exist. Okay, so what went wrong here? Well, if we go back to the conditions, see here, look at condition number 3, that g prime, that denominator, must be non-zero for all x except at c, possibly. Now, if we look at this denominator over here, when we look at g prime, you can check this, or you can plot it on Desmos, you can have a look. That is not non-zero for all x on that domain. Okay, so check that bottom there, you can plot it on Desmos. Okay, you all know how to do that by now. You'll see it's actually, some of it's positive, some of it's negative. There's a problem there. Okay, so you can check that. So here, plots on Desmos. And check g prime of x not being 0. Okay, there's going to be a problem then. Okay, number 3. We have the limit as x goes to infinity of x plus sine x over x. Okay, so let's go through the conditions. We'll check condition number 1. The top and the bottom must be both 0 or both infinite. When x goes to infinity, the top is infinite, the bottom is infinite. That's fine. Let's check if they're differentiable. Yes, the top is differentiable, the bottom is differentiable. That's fine. Okay. When x goes to infinity, is the bottom non-zero? X, it's a positive number. X goes to infinity, it's positive. Okay, so it's non-zero. That's fine. So we go through the whole list over here. So we've checked everything except that last thing. Let's go and check that. Everyone with me on checking those 3? Yes. Okay. So this is going to be the limit as x goes to infinity, the derivative of the top and the derivative of the bottom. So that's going to be x plus sine x prime over x prime. So this will be, again, question mark, because this is completely wrong. So this will be the limit as x goes to infinity. The derivative of the top, that will be 1 plus cos x. The derivative of the bottom, that's just 1. Okay, so this is going to be the limit as x goes to infinity, 1 plus cos x. But this limit does not exist. Cos x will go between minus 1 and 1 constantly. So when x goes to infinity, it still goes between minus 1 and 1. There's no limit to this. So here, limit does not exist. Now, if you just left this as an answer, it's completely wrong. Why? Well, the condition says, fourth condition, the limit must exist. We've just shown the limit doesn't exist, so L'Hopital's rule could not be used. So instead of using L'Hopital's rule, we're going to try something else. So we have the limit as x goes to infinity, x over x, that's going to be a 1, plus sine x over x. So this will be the limit. So we can take the 1 out. That has nothing to do with the limit. So it's going to be 1 plus the limit as x goes to infinity, sine x over x. You can use the squeeze theorem. You show that sine x over x will be 0. Okay, I hope you haven't forgotten about the squeeze theorem. Okay, so here we get the limit is 1. So that's the correct answer. If we use L'Hopital's rule, we get does not exist, but that's completely wrong. Why? Well, we didn't check condition number 4. The limit must exist. In this case, the limit doesn't exist, so L'Hopital's rule cannot be used. Okay, so big exclamation mark, check the conditions. Okay, so in the quiz, test, exam, whatever, if I give you a limit question and you use L'Hopital's rule on something that can't use L'Hopital's rule, well, you just get 0 because you never check the conditions. Okay, so please be careful about that. So make sure if you're going to use L'Hopital's rule, make sure you can use L'Hopital's rule. Otherwise, you get 0 because it's all wrong. Okay, so please check the conditions. Okay, let's have a look at some examples. Okay. Now, for all of these examples, you can use L'Hopital's rule. Obviously, it's examples for L'Hopital's rule. But again, you need to check the conditions. So for all of these, you can use L'Hopital's rule, right? It's part of the examples. However, you do need to check. So on the side, just make a note. Condition 1, 2, 3, 4, and then put a tick. Condition 1, yes, no. Condition 2, yes, no, and so on. The reason is, for class test 2 and the exam and so on, I'm just going to give you a whole lot of limits. And the question is, evaluate the limits. I'm not going to tell you use the limit laws. I'm not going to tell you use squeeze theorem. And I'm not going to tell you use L'Hopital's rule. You need to figure that out on your own. Okay. So for all of these, you can use L'Hopital's rule, but for tests, exams, and so on, it's all mixed. Okay. Some of them will use L'Hopital's rule, some of them won't. It's up to you to figure out. And the only way to be sure you're doing the right thing is to check the conditions. Otherwise, it's all wrong, you get 0. Okay, number 1, we have the limit as x goes to 0, arctan of x over x. So I'll check the first 2 conditions, and then you can do the next 2 for homework. And then for the rest of them, I'll point out some of the important conditions, and then the rest I'll leave for you. Okay, so first condition, do we get 0 over 0? Okay, arctan of 0 is? Tan of 0 is? Tan of 0 is 0. So arctan of 0 is 0. Okay, you just go back and forth. Or you use your calculator. You've got the inverse functions on there. Okay, in the bottom, when x is 0, bottom is 0. So we end up with 0 over 0. Okay, so that's good. 0 over 0. Condition 1, check. Condition 2, are they differentiable? Arctan, can we take the derivative? Yes, we did that last week. Okay, x, can we take the derivative? Yes, so condition 2, check. Okay, and then you can check condition 3 and 4 for homework. Okay, first 2 conditions check, the other 2 you can check that, but they are satisfied. So what we do is we take the derivative of the top and the bottom. So this is equal to the limit as x goes to 0. The derivative of arctan, 1 over 1 plus x squared. Okay, so everyone should have the table of derivatives now. So when we're going through these problems, you can just go back, look at the table, and see what it is. Okay, so arctan, you go back to what we did last week with that big table that you drew up, and you just check. Okay, you do that enough times, you end up memorizing it, which is the goal. Okay, bottom, derivative of x, 1. Easy. Okay, so just by the way, for these problems, you're going to have a lot of fractions divided by fractions. So please keep in mind your algebra with this. Okay, so for example, if you have a over b divided by c over d, this is a over b times d over c. Okay, please don't screw that up, right? If you have a fraction divided by a fraction, that is multiplied by the reciprocal. Okay, if you mess up the algebra, everything after that is wrong. Okay, so please keep that in mind, right? The algebra with fractions over fractions. Okay, so here it's not so bad because we're just dividing by 1, so that's fine. So that is the limit as x goes to 0, 1 over 1 plus x squared. Here we don't have to worry about anything. If x is 0, it's just 1 over 1, so it's 1. Easy stuff. Number 2. So we have the limit as x goes to 0 plus. Okay, we all know what that means. 0 plus, 0 minus. Of x times the natural log of x. Okay, let's check condition 1 and 2. Okay, so we've got x times the natural log of x. When x goes to 0, x in the front will be 0 times. Okay, and then when x goes to 0, the natural log of x goes to minus infinity. Right, you have that asymptote there. Right, your natural log looks like that. Okay, and then you got that asymptote at 0. Okay, so it's an indeterminate form, 0 times infinity. Now, that's not what we want for L'Hopital's rule. If we go right back up here, okay, it is an indeterminate form, that third one over there, 0 times infinity. However, for L'Hopital's rule, we need 0 over 0 or infinity over infinity. Okay, so what we need to do, go back here, is somehow convert this from one indeterminate form to another indeterminate form. And that's just some algebra that we need to do. There's some tricks to it, so I'll show you for this one, and then the others we'll do tomorrow. So this will be the limit as x goes to 0 plus. The natural log of x, we're going to keep that at the top. And then we're going to divide by 1 over x. Okay, I told you, fractions over fractions, you're going to see that a lot. Now, the natural log of x divided by 1 over x, that's multiplied by the reciprocal. So it will end up being x times the natural log of x, which is what we have at the beginning. So I haven't changed anything. It's still the same function. But now let's check what happens with the limit. In the top, when x goes to 0, the natural log goes to minus infinity. Okay, and then in the bottom, when x goes to 0, 1 over x goes to, if you're dividing by 0, it goes to infinity. Okay, so we have infinity over infinity. That's what we need. Okay, we need that infinity over infinity or 0 over 0. Must be one of them. If it's not, you need to do some work to make it look like that. Okay, so now we can use L'Hopital's rule. So previously we couldn't. It's not the right form. Do some algebra. Now it is the right form. So this is the limit as x goes to 0 plus. Now we need to do the derivative of the top and the derivative of the bottom. The derivative of the natural log of x is 1 over x. Good. And the derivative of 1 over x? Yeah. There you had it. 1 over x squared. Good. Both the minus sign, because it's x to the minus 1. Remember to take the minus down. So it's minus 1 over x squared. And again, we've got this fraction over a fraction. So please be careful with your algebra. So this is going to be the limit as x goes to 0 plus. The x squared goes to the top. So x squared over x, that's going to be minus x. Now we have no problems. When x goes to 0, that goes to 0. Okay, now we end up with that. Okay, so please remember this trick over here. Okay, if you have a product of things, you can always take it down to the bottom by taking the reciprocal. So if it was x squared natural log of x, you could then divide by 1 over x squared. That's the same thing as multiplying by x squared. Okay, so please remember that. This trick is used quite a lot for these types of problems. Any questions on that? The dividing by 1 over x? All good. Okay. Number 3. Limits x goes to infinity of 3x squared plus 1 over 2x squared plus x. Okay, let's check the first 3 conditions. The last one, I'll leave that for you. Okay, first condition. The top and the bottom must be infinite or 0. When x goes to infinity, the top will be infinite, right? X squared, that'll be infinite. The bottom will be infinite. So that's condition 1, check. So that's number 1. Number 2, are they differentiable? Yes. Quadratic, of course it's differentiable. Check. That's the second one. Let's go back to the list so you can see. Yeah, check. Next, G prime must be non-zero. Let's see what G prime is. Go down here. That will be 4x plus 1. Is that going to be positive? 4x plus 1. X is positive. X goes to infinity. You substitute something. Is it non-zero? Okay. G prime of x is 4x plus 1. If I put in 3, is it non-zero? If I put in 4, is it non-zero? If I put in anything going to infinity, is it non-zero? Yeah, so it's non-zero. So check. Okay, that was the third thing. And then the fourth thing we'll check now, does the limits exist? We'll see that. Okay, so again, please go through that checklist. So this is going to be equal to the limit as x goes to infinity, 3x squared plus 1 prime over 2x squared plus x prime. So this will be limit x goes to infinity. The derivative of the top, that will be 6x. Okay, and then the derivative of the bottom, it will be 4x plus 1. Okay, now we're stuck a bit. If we take the limit as x goes to infinity, the top is infinite, the bottom is also infinite. But the nice thing is we can just use L'Hopital's rule again. We've used it once, and we end up with a problem where we can use it again. You can go through the checklist. The top is infinite, the bottom is infinite, check. Top is differentiable, bottom is differentiable, check. Okay, the bottom is non-zero. When you take the derivative, check. We can use L'Hopital's rule again. So this is going to be the limit as x goes to infinity. The derivative of the top, that will be a 6. Derivative of the bottom, it's a 4. So that will be 6 over 4, or you can write it 3 over 2. Okay, so you can do it like that. So L'Hopital's rule, that gives us 3 over 2. Now, we've done this one before. We can actually do this a different way. So big or, we can do it another way. So we can write this as the limit as x goes to infinity. At the top and the bottom, we can factor out an x squared. Right. That was before, when we had these limits. X squared at the top, x squared at the bottom, they can go. So we end up with the limit as x goes to infinity, 3 plus 1 over x squared over 2 plus 1 over x. Now when x goes to infinity, 1 over x squared, that's going to go to 0. Then 1 over x, that also goes to 0. And we're left with 3 over 2. Which is exactly what we got with L'Hopital's rule. So for some of these limit problems, there's multiple ways of solving them. You can use our limit laws like we have on the right, or you can use the L'Hopital's rule like we have on the left. You get the same answer. Any questions on this? All good. Okay. Always keep in mind when you can do things multiple ways. If you forget the one way, at least you can do the other way. If you forget both ways, then you're stuck. Okay, number 4, we have the limit as x goes to 0 of e to the x minus 1 over x squared plus x. Okay, so we'll just go through condition 1. The others you can check. So when x goes to 0, the top will be 1 minus 1. That will be 0. When x goes to 0, the bottom will be 0 plus 0. That's going to be 0. So this is 0 over 0. That's what we want. It must be either 0 over 0 or infinity over infinity. Condition 1, check. You can check the others for yourself. Okay, so we can use L'Hopital's rule. So this will be the limit as x goes to 0, e to the x minus 1 prime over x squared plus x prime. So this will be the limit as x goes to 0. The derivative of the exponential is the exponential, so that just stays. The derivative of -1, that's 0. You can just leave it out. Okay, and then in the bottom, x squared, you take the 2 down, so that will be 2x. And the derivative of x, that's 1. Okay, let's check. X goes to 0. E to the 0, that's 1. 2 times 0, that will be 0. And we're left with a 1. So we have 1 over 1, which is just 1. Okay, so we get the answer 1. Okay, last one for today, number 5. We have the limit as x goes to infinity of x e to the minus x. Okay, again, we need to check the conditions. I'll check one for you, you check the others. So when x goes to infinity, x, that will be infinite. E to the minus x, that will be 0. So this will be infinity times 0. So it's an indeterminate form, that's fine, but it's not the correct one. What we want is 0 over 0 or infinity over infinity. This doesn't work. So what we can do instead, e to the minus x, that's a negative exponent, we can put it down to the bottom. So this will be the limit as x goes to infinity. The x, that can stay at the top. E to the minus x, that can go down to the bottom. That will be e to the x. Let's check again. So when x goes to infinity, the top is x, so that's infinity. E to the x, when x goes to infinity, that is also infinity. So infinity over infinity. Okay, condition 1 is now satisfied. Okay, and again, we've got this trick of putting it down to the denominator. Okay, please remember that. Okay, so that's the same as what we did with that problem 2. You take it down to the denominator, and you end up with 0 over 0 or infinity over infinity. Condition 2, 3, and 4, I'll leave that for you to check. Okay, but it works, so you can check that. It works fine. So we can use LHopitals rule. So there'll be limit x goes to infinity. The derivative of x, that's 1. And the derivative of e to the x, just e to the x, stays the same. Okay. Now, when x goes to infinity, e to the x also goes to infinity. So what happens if we have 1 over infinity? 0. Good. Now we get 0. Okay. Any questions on these ones? That's all good. Okay. I'll leave you with some homework problems to try out. And then we'll finish off with the more difficult ones tomorrow. So these ones were pretty easy. It was something over something, pretty straightforward. Tomorrow we'll have a look at these other ones here. So the infinity minus infinity, or the 0 to the 0, 1 to the infinity, those ones we'll look at tomorrow. Okay, but some homework for you to try. Okay, number 1, we have the limit x goes to infinity, 1 plus 1 over x to the x. Okay, so when x goes to infinity, the inside part will be 1, because the 1 over x will be 0, and the exponent will be infinity, so it will be 1 to the infinity. That's one of those indeterminate forms, the second to last one. Yeah, so you can try that one for homework. And then tomorrow we'll go through all of it properly. Okay, number 2, we have the limit x goes to 1, x over x minus 1 over the natural log of x. Okay, this will be like a infinity minus infinity type problem. You can try that out. Okay, number 3, limit x goes to 0 plus of x to the x. So this will be a 0 to the 0 type problem. Okay, so if you did the textbook reading, you should be able to do these. But tomorrow we'll go through all of that again. Okay, and remember the other homework for those 5 problems we had earlier, check those 4 conditions. So for some of them, I did 2 of them or 3 of them. Go over all of those again and check the 4 conditions. Okay. Any questions on what we covered today? Yes. No. Technically not. You can make it 1, but in some cases it's not 1. Okay. But good question though. Okay. Any other questions? No. Okay. So we'll leave it at that for today. Tomorrow we'll go through these homework problems, and then there's another 7 that we'll go through. Okay, but after that, you should be able to do the tutorial.